All right, let's jump right in with a question that sounds simple, but the answer might just change how you see everything. Is the stuff all around us actually pure?
I mean, think about it. You go to the store and you see labels all the time that say things like pure milk or pure salt. But is the milk sitting in your fridge or the salt in your shaker, is it really pure?
You see, for most of us, pure just means, it's not contaminated. Nothing bad has been added. But for a scientist, the definition is way stricter. And by that scientific definition, believe it or not, pretty much everything you see here, nope, not pure at all. So here's the deal. Scientifically speaking, something is pure only if it's made of a single type of particle, just one. So think about a sugar cube. That's pure. Why? Because it's all just sugar molecules, all the same. But milk? No way. It's a whole party in there. Water, fat, proteins. You see what I mean? And that key difference is exactly what we're going to break down.
Okay, so here's our game plan. First, we'll nail down what pure actually means. Then we'll look at the two big categories everything fits into. We'll take a closer look at mixtures, then peek inside pure substances. And to wrap it all up, we'll have a final showdown to make sure it all makes sense. Sound good? All right, let's start with the big picture. It's actually pretty cool. Turns out, you can sort all the stuff in the entire universe into just two main buckets.
And this flowchart right here, this is going to be our map. You can see how everything, all matter, starts at the top. And then boom, it splits into two big paths, pure substances on one side and mixtures on the other. We're going to start our journey on the right with mixtures, because honestly, that's the stuff we run into all the time.
So what exactly is a mixture? Well, it's pretty simple, really. It's just stuff made of more than one kind of pure thing all jumbled together. The ocean, the dirt under your feet, heck, even the air you're breathing right this second. It's all mixtures. Now, mixtures themselves come in two main flavors. You've got your homogeneous mixtures, where everything is blended so perfectly it all looks like one thing. Like when you dissolve salt in water, you can't see the salt anymore, right? And then you have heterogeneous mixtures. This is where you can totally see the different parts. Imagine mixing sand and salt. You can still see the individual grains of both. Okay, let's zoom in a little bit further. Because within these two big types, there are three key kinds of mixtures we need to know about: solutions, suspensions, and colloids.
First up, we have solutions. A solution is a homogeneous mixture, meaning it's perfectly blended. The particles are so tiny you just can't see them. Salt water is a classic example. So is lemonade. And here's a fun one. Even some solids are solutions. Things like brass. That's actually a solution of one metal dissolved in another.
Okay, next on our list is a suspension. Now this is a heterogeneous mixture. The particles in here are bigger, and they don't actually dissolve. They just kind of hang out, suspended in the liquid. A perfect example is muddy water. If you just leave it alone for a while, what happens? All the mud settles right down to the bottom. And that brings us to the really cool one, the one in the middle, the colloid. Now, colloids are masters of disguise. Why? Because they look homogeneous. They look perfectly blended, just like a solution. But secretly, on a microscopic level, they're actually heterogeneous. And yep, you guessed it, our friend milk is the star example of a colloid. So you might be wondering, if it looks like a solution, how on earth do we know it's not? How do we blow its cover? Well, it turns out the secret weapon is a simple beam of light. This is something called the Tyndall effect. Take a look here. In a true solution, you shine a light through it and you can't see the beam. It just passes straight through. But now, look at the colloid. The particles in there are just big enough that they scatter the light. And because of that, you can see the path of the beam crystal clear. Pretty neat, huh? And I guarantee you've seen this out in the real world. Ever seen those beautiful sunbeams slicing through a foggy forest? Or the light from a projector cutting through a dusty room? That is the Tyndall effect. The fog or the dust is a colloid, tiny particles suspended in the air, and they're scattering the light, making those beams visible.
Okay, so we've pretty much covered the world of mixtures. Let's go back to our map, our flowchart, and this time we're going to head down that other path, the world of pure substances.
The first kind of pure substance we're going to talk about is the most fundamental of all, an element. These are the Lego bricks of the universe. Think gold, iron, oxygen. You can't break them down into anything simpler through a chemical reaction. An atom of gold is, well, it's just an atom of gold. That's it.
So what happens when these elemental building blocks join forces? When they chemically bond together, you get a compound. Now, a compound is still a pure substance because all its particles are identical. But each of those particles is made of two or more different elements stuck together in a very specific, fixed recipe. The most famous example, of course, is water, H2O. It's always two hydrogen atoms chemically bonded to one oxygen atom. Always.
All right, we've been down both paths of our map. We've seen mixtures, we've seen pure substances, so now it is time for the final showdown. Mixture versus compound. Let's really nail down the difference.
Okay, let's break this down. In a mixture, things are just mixed together. No new substance is formed. But in a compound, the elements actually react to create something brand new. With a mixture, you can have a little salt or a lot of salt in your water. The composition is variable. But with a compound, like water, the recipe is always fixed. H2O, period. Here's a big one. A mixture keeps the properties of its parts. Salt water is still salty and it's still wet. But a compound, it's a totally new thing. Water is nothing like the explosive hydrogen and the flammable oxygen that make it up, right? And finally, you can usually separate a mixture with physical means, like evaporation or a filter. But to break a compound apart, you're going to need a chemical reaction to break those bonds.
So if you're going to remember just one thing from all this, let it be this. Mixtures are simply blended, but compounds are chemically bonded. That's the whole ballgame. It's kind of like the difference between a random group of people standing in a room and a tightly knit family holding hands.
And that brings us full circle. So the next time you pour a glass of milk, or just take a deep breath of fresh air, or stir some sugar into your tea, I want you to stop for just a second. Now that you know the difference, what do you actually see? Do you see a solution? A colloid? Is it just a simple blend? Or is there a powerful chemical bond at work?